Welcome to the Fall Asleep Fast channel. On this night, when the stars are whispering, allow me to use this bedtime science video to lay out a cosmic blanket for you now. Please close your eyes and imagine we are riding the moonlit boat of an astronomy bedtime video, drifting in the cradle of the Orion Nebula. Those twinkling stars are not distant scientific symbols, but a customized lullaby of constellations. Just for you, the heartbeat of Betelgeuse transforms into pulsating rhythms. Jupiter's clouds swirl with milky light vortices, and Saturn's rings sing billions of ice crystals into a cosmic cradle song. The acceleration of the Milky Way's rotation syncs with your breath, and the dust left behind by supernovae reconstructs into the fabric of dreams during meditation. We are no longer mere observers, but stardust floating in the afterglow of creation, letting Einstein's curvature of space-time gently envelop your weary neurons. As the Pleiades bloom with blue light in your mind, allow the boundaries between scientific principles and dreams to dissolve tonight. There is no need to ponder the singularity of black holes. Simply let the waterfall of light from the Andromeda galaxy wash away the day-ass distractions. For all unsolved mysteries will transform into metaphors for slumber within the starlit cushions of the sleepy science channel. Good night, dear cosmic wanderer. May this bedtime science video escort your consciousness into a sweet dream, more serene than dark matter. Imagine this measuring an object so fast it could circle the Earth 7.5 times in just 1 second. How difficult would that be? For thousands of years, humans believed that light traveled instantaneously. A star would flicker and its light would immediately reach the human eye. But several brilliant scientists refused to accept this assumption. Through a series of ingenious experiments, they uncovered one of the universe's most fundamental constants today. We will explore together the fascinating story of how humans measured this cosmic speed limit. This quest revolutionized physics, made global positioning systems possible, and revealed the true nature of space and time itself. In the 5th century BC, the ancient Greek philosopher Empedocles first proposed that light might have a finite speed. He believed that light was some kind of substance traveling from the sun to the earth. Although he couldn't verify this radical idea, Aristotle disagreed. He argued that light existed instantaneously, a state of being, not a motion. This debate persisted for nearly 2,000 years. The first serious attempt to measure the speed of light was made by Galileo around 1638. Picture this scene. Galileo and his assistant stood on hilltops about 1.6 kilometers apart, each holding a lantern with a shutter. Galileo would uncover his lantern, and as soon as the assistant saw the light, he would immediately uncover his own. Galileo hoped to calculate the speed of light by measuring the time difference between uncovering his lantern and seeing his assistant's response. This experiment failed, not because the method was flawed, but because light took only about 5 microseconds to travel that distance, far faster than human reaction times could detect. Yet Galileo's failure brought a crucial insight. If light truly had a speed, it must be astonishingly fast. This realization shifted the question from whether light had a speed to how we could measure such an incredible velocity. The answer eventually came from observing celestial bodies, not from Earth itself, Danish astronomer Ole Ragnar, working at the Paris Observatory, was studying Jupiter's moon Io in 1676. He carefully recorded the times when Io was eclipsed by Jupiter. As it orbited the planet, he noticed a peculiar pattern. When Earth moved closer to Jupiter in its orbit, Io's eclipses occurred earlier than predicted. When Earth moved away from Jupiter, the eclipses were delayed. This wasn't an observational error, it was a clue to a fundamental constant of nature. Ragnar realized that if light had a finite speed, this pattern made perfect sense. When Earth was closer to Jupiter, the light from Io's eclipse had a shorter distance to travel, so it arrived earlier when Earth was farther away. The light took longer to reach us. By comparing the timing differences of Io's eclipses over one Earth orbit around the Sun, Ragnar calculated that light took about 22 minutes to cross the diameter of Earth's orbit. From this, he derived humanity's first quantitative estimate of the speed of light, about 220 kilometers per second. Considering the limitations of his tools, this value was remarkably close to the actual speed of light. The scientific community was initially skeptical, as the idea that light had a measurable speed challenged centuries of accepted belief. But Ragnar's predictions of future Io eclipses proved accurate, forcing scientists to accept this revolutionary idea. Light does not travel instantaneously, it is fast but finite. This discovery completely reshaped astronomy. Astronomers realized that the celestial objects they saw were not as they are now, but as they were when their light began its journey. In 1728, James Bradley, through another celestial observation, further confirmed the finite speed of light. He discovered the aberration of starlight as Earth orbits the Sun. The apparent position of stars shifts slightly. Imagine standing in the rain. If you stand still, rain falls vertically, but when you run, the rain appears to fall at an angle. The same happens with starlight as Earth moves through space. The starlight we see at different times of the year appears to come from slightly different directions. By measuring this aberration effect, Bradley independently calculated the speed of light, corroborating Ragnar's earlier work. These astronomical methods, though ingenious, were indirect measurements. Scientists longed to measure the speed of light directly on Earth. In 1849, Hippolyte Fizeau achieved this breakthrough. His experimental setup was clever and highly precise. A beam of light passed through the gap of a rapidly rotating toothed wheel, traveled 8 kilometers to a mirror, and was reflected back. If the wheel's rotation speed was just right, the returning light would pass through the next gap. If the rotation was slightly faster or slower, the light would be blocked by a tooth of the wheel. Imagine this experiment in the French countryside. Fizeau placed a light source and the rotating wheel at one observation point, while his assistant placed a precisely aligned mirror 8 kilometers away. By adjusting the wheel's rotation speed until the reflected light passed perfectly through a gap, Fizeau could calculate the time it took for light to travel the 16-kilometer round trip. He obtained a value of 315,000 kilometers per second. Not perfect, but very close to the true speed of light. And this result was achieved entirely on Earth without astronomical observation. In 1850, Leon Foucault improved on Fizeau's method by replacing the toothed wheel with a rotating mirror. His setup was more compact and could be operated indoors. Avoiding atmospheric interference in his experiment, a beam of light was directed onto a rapidly rotating mirror, reflected to a fixed mirror, and then reflected back to the rotating mirror. While the light traveled, the rotating mirror would turn slightly, causing the returning beam to be deflected. By measuring this deflection and combining it with the rotation speed of the mirror, Foucault calculated a speed of about 298,000 kilometers per second, within 1% of the modern value. And here the story takes an exciting turn. Foucault noticed an unexpected phenomenon. Light traveled slower in water than in air. This observation contradicted Newton's corpuscular theory of light and supported the wave theory of light, fundamentally changing our understanding of light's nature. A simple measurement of the speed of light had revealed a fundamental question about the essence of light itself. For American physicist Albert A. Michelson, measuring the speed of light became a lifelong pursuit. He devoted his life to this challenge. In 1878, as a young naval officer, Michelson improved Foucault's rotating mirror method, greatly increasing its precision. He set up his apparatus in a shed at the United States Naval Academy in Annapolis, using an octagonal rotating mirror and extremely precise measuring instruments. He eventually obtained a value of 299,910 kilometers per second, the most accurate measurement of the time. His relentless pursuit of precision led Michelson to develop even more refined instruments. He realized that measuring the speed of light was not just about curiosity. It was key to understanding the fundamental nature of the universe. The interferometer he designed could measure tiny differences in the travel time of light, with accuracy on the order of the wavelength of light. This astonishing precision soon led to one of the most important experiments in the history of physics. In 1887, Michelson collaborated with Edward Morley on an experiment that would shake the foundations of physics. Scientists at the time believed that waves required a medium to propagate. They called this hypothetical medium the luminiferous ether, an invisible substance permeating the universe. If the ether existed, then as Earth moved through it, it would create an ether wind that would affect the speed of light in different directions. The Michelson-Morley experiment was elegantly simple in principle, but required extreme precision to execute. They split a beam of light into two perpendicular paths. After reflecting off mirrors, the beams recombined, forming an interference pattern. If Earth's motion through the ether caused the two beams to travel at different speeds, the interference pattern would shift. They rotated the entire apparatus and repeated measurements at different times of day and different seasons of the year to account for Earth's rotation and revolution. The results shocked everyone. There was no shift, no matter how they rotated the apparatus or when they measured. The speed of light remained the same in all directions. There was no ether wind, no preferred reference frame. Light did not behave like sound or water waves. It was something entirely new. This failed experiment became one of the greatest successes in scientific history. It provided key evidence for Einstein's special theory of relativity, while physicists struggled to understand the implications. Engineers continue to refine techniques for measuring the speed of light. In 1926, Michelson conducted the most ambitious measurement of his career, using Mount Wilson and San Antonio Mountain in California as observation points. He established a 22-mile baseline between the peaks, bouncing light between precisely positioned mirrors. The long measurement baseline greatly improved timing accuracy. His final value, 299,796 kilometers per second, a figure accepted by the scientific community for many years. Advances in electronics revolutionized the measurement of the speed of light. In 1947, Louis Essen and Albert Gordon Smith used a cavity resonator. By measuring its resonant frequency and dimensions, they could calculate the speed of light with unprecedented accuracy. This method worked because light is an electromagnetic wave, and radio waves, microwaves, and visible light are all electromagnetic radiation traveling at exactly the same speed. The story grew even more fascinating. In 1958, Keith Froome used a microwave interferometer to achieve even greater precision. But the real breakthrough came from an unexpected field. In 1960, the invention of the laser suddenly gave scientists an ideal light source with perfect coherence, monochromaticity, and precise control. In 1972, a team led by Kenneth Evanson at the U.S. National Bureau of Standards achieved a remarkable feat. They measured both the frequency and wavelength of a laser with extremely high precision, then multiplied the two values. The beauty of this method lay in its directness. No complex indirect derivation was needed to find the speed of light. Their measurement was so precise that it revealed a problem. Since 1791, the definition of the meter had been based on a metal bar, and this physical standard could no longer meet the demands of modern precision. This issue led the scientific community to make a monumental decision in 1983. Instead of continuing to refine measurements of the speed of light, they would define the speed of light as an exact value and redefine the meter based on this constant today. The speed of light is defined as exactly 299,792,458 meters per second, and the meter is defined as the distance light travels in vacuum. In 1 to 199th, 792,458 of a second, consider the significance. Our measurement of the speed of light has become so precise that it now underlies our unit of distance. The speed of light has become a central constant in our measurement system, joining a handful of other natural constants as the foundation of our understanding of the physical world. This is not just a triumph of scientific precision, it carries philosophical weight. It defines the fundamental properties of the universe as we perceive it. Modern measurement techniques have pushed precision to astonishing levels. Scientists now use optical frequency combs, laser sources that emit thousands of precisely spaced spectral lines like the teeth of a comb. This tool, which earned the 2005 Nobel Prize in Physics, enables frequency measurements accurate to 15 decimal places. Today, we no longer need to measure the speed of light, but we use these technologies to measure other fundamental constants with the same precision. Recent experiments with exotic materials have added new twists to the story. Scientists have used Bose-Einstein condensates to slow light to walking speeds. In 1999, Lienhaus team at Harvard University slowed light to just 17 meters per second, and later even brought light to a complete stop, storing its information in atomic states. These experiments do not change the fundamental speed of light in vacuum, but reveal new ways light can interact with matter, ways that would seem like magic to early scientists. Meanwhile, other researchers have developed materials with negative refractive indices, in which light appears to travel in the opposite direction. Metamaterials can also bend light in seemingly impossible ways, enabling invisibility cloaks and superlenses. These advances show that although the speed of light in vacuum is constant, our ability to manipulate light's behavior continues to expand in astonishing ways. The significance of measuring the speed of light extends far beyond pure science. Every time you use your phone's GPS, you rely on our precise knowledge of the speed of light. GPS satellites send signals that travel at the speed of light. Your phone measures tiny time differences in signals from multiple satellites to calculate your position. If the finite speed of light and relativistic effects were not accounted for, GPS would accumulate errors of about 10 kilometers per day. Consider how accurately we now understand the speed of light. The Large Hadron Collider at CERN accelerates protons to 99.9999% of the speed of light. At that speed, protons are only 3 meters per second slower than light. The collider's timing system must be accurate to picoseconds. 1 picosecond compared to 1 second is like 1 second compared to 32,000 years. That is the level of precision required in modern physics. The measurement of the speed of light has also revealed profound truths about the universe. When we observe the Andromeda Galaxy to 0.5 million light years away, we see it as it was to 0.5 million years ago, a time when early humans were just beginning to use stone tools. Light from distant quasars has traveled for billions of years, carrying information from the early universe. All astronomical distance measurements rely on our knowledge of the speed of light. In 1905, Einstein's special theory of relativity transformed the constancy of the speed of light from a puzzling measurement result into a fundamental physical principle. Einstein realized that if the speed of light is the same for all observers, then space and time themselves must be flexible. Moving clocks run slow, moving rulers contract. The speed of light is not really about light, it is the ultimate speed limit. For information or causality in the universe, light travels at this speed because photons have no mass. In 2017, observations by LIGO confirmed that gravitational waves also travel at exactly the same speed. Gravitational waves and light from a neutron star merger traveled 130 million light years and reached Earth almost simultaneously. This universal speed limit shapes everything in the universe. It explains why the night sky is dark, ensures the orderly sequence of cause and effect, and defines the observable universe. The speed of light is a fundamental constraint of the cosmos, a rule that maintains the logical consistency of reality. Modern quantum experiments have revealed even stranger aspects of light's behavior. Quantum entanglement seems to create instantaneous correlations between distant particles, yet no information is transmitted faster than light. Scientists have achieved quantum teleportation between laboratories and even between satellites and ground stations. But without breaking the light speed barrier, these experiments show that the universe maintains a delicate balance between known locality and the light speed limit, allowing quantum correlations without violating causality. Recent experiments have further expanded our understanding. Scientists have developed slow light glass, in which light takes seconds or even minutes to travel a few centimeters. They have also created light pulses that appear to exit a material before fully entering it, seeming to travel faster than light. But careful analysis shows that no information actually exceeds light speed. These experiments help us understand the subtle differences between phase velocity, group velocity, and information velocity. Today, the most precise measurements often combine multiple techniques. The International Bureau of Weights and Measures maintains the world's most accurate atomic clocks with precision such that they would not gain or lose a second. In hundreds of millions of years, these clocks define time by measuring the frequency of light emitted by cesium atoms. Cesium atoms oscillate 9,192,631,770 times per second, and this frequency defines 1 second. Combined with interferometry that can measure distances on atomic scales, we achieve levels of precision that early scientists could hardly imagine. Space-based observations have opened new frontiers in the study of light speed. Lunar laser ranging experiments use reflectors placed on the moon by Apollo astronauts to measure the round-trip time of laser pulses, determining the Earth-Moon distance with millimeter precision. This experiment not only tests Einstein's theories with extreme accuracy, but also reveals that the Moon is moving away from Earth at 38 millimeters per year. All these measurements rely on the precise definition of the speed of light. The cosmic microwave background radiation provides another window into the behavior of light. These ancient photons have traveled for 13.8 billion years, redshifting from hot radiation to cold microwaves. The Planck satellite mapped tiny temperature variations in this radiation, revealing the composition and age of the universe. Every step in interpreting this data relies on the assumption that the speed of light has remained constant throughout cosmic history. Future missions will further improve measurement precision. The Laser Interferometer Space Antenna will deploy multiple spacecraft in space, using laser beams millions of kilometers long to detect gravitational waves. Space-based atomic clock arrays will test whether fundamental constants, including the speed of light, vary with time or gravitational fields. These experiments will explore whether the laws of physics are truly constant or slowly evolving. The finite speed of light also carries deep philosophical implications. We can never see the present. All observations are of the past. The sun we see is 8 minutes old. Your reflection in a mirror is nanoseconds old. Even the electrical signals in your brain are limited by the speed of light at the molecular level. We live in a universe where the present is fundamentally inaccessible. All observation is archaeology of light's history. Looking back at the history of measuring the speed of light, we see the essence of scientific progress. It took millennia for humans to realize light has a speed, centuries to measure it roughly, and decades to reach modern precision. Each advance required new technology, new thinking, and often accepting that previous beliefs were wrong. The story of measuring the speed of light is, in essence, the story of science itself, patient, step-by-step exploration, steadily approaching the truth, from lantern experiments on hilltops to quantum labs manipulating single photons. Humanity's journey to measure the speed of light has come a long way today. Scientists can count individual photons, measure their arrival times with femtosecond precision, and even encode information in their quantum states. We have come so far that the challenge is no longer measuring the speed of light, but understanding what this universal constant truly means for the nature of reality. Let's also consider how different cultures and civilizations have explored this puzzle. In the 11th century, Islamic scholar Ibn al-Haytham argued that light must have a finite speed, since vision depends on light traveling from objects to the eye. Such cross-cultural parallel discoveries show that the speed of light is a truly universal question, one that sparks human curiosity in every era and every part of the world. The technological revolution sparked by understanding light speed continues to this day. Fiber optic cables carry information at about 70% of light speed in glass, forming the backbone of the internet. Every email, every video stream, every call travels as pulses of light along these glass highways. The entire global communications network depends on our precise knowledge of how light travels through different materials. In medicine, light speed has enabled breakthrough technologies. Optical coherence tomography uses the travel time of light to generate 3D images of living tissue, allowing doctors to examine the retina or detect cancer without surgery. Laser surgery relies on precise timing of light pulses to cut tissue without damaging surrounding areas. Every calculation in these technologies requires knowing exactly how fast light travels through different parts of the human body. Measuring the speed of light has also transformed our understanding of the very large and the very small in cosmology. Typeus supernovae serve as standard candles. Their apparent brightness reveals their distance, but this method depends on accurately knowing the speed of light using such measurements. Scientists discovered that the universe is expanding at an accelerating rate, driven by mysterious dark energy, a discovery that earned the 2011 Nobel Prize in Physics. Without precise knowledge of the speed of light, this would have been impossible on quantum scales. The speed of light determines the basic structure of atoms. The fine structure constant, which involves the speed of light, governs the strength of interaction between electrons and photons. This seemingly arbitrary constant explains why atoms are stable, why chemical reactions proceed as they do, and even why life is possible. If the speed of light were different, the fine structure constant would change. and atoms and everything made of them might not exist. Recent experiments continue to push the boundaries of our knowledge. Scientists have stopped light storing photon quantum information in atomic clouds and releasing it later. They have made light travel through highly dispersive materials, causing different colors to arrive seconds apart. They have created vortex beams that carry orbital angular momentum, rotating like propellers as they travel. Each discovery reveals new dimensions of light's behavior while reaffirming the unbreakable nature of its fundamental speed limit. Exploring whether the speed of light varies has become an important research direction. Some theories suggest that fundamental constants, including the speed of light, might change over cosmic time or in different regions of the universe. Astronomers analyze light from distant quasars, looking for subtle shifts in spectral lines that might indicate different physics billions of years ago. So far, the speed of light appears constant, but the search continues with ever greater precision. The intersection of light speed and quantum mechanics has yielded astonishing phenomena in quantum tunneling. Particles seem to instantly cross barriers, yet no information travels faster than light. Quantum entanglement allows instantaneous correlations between distant particles, but cannot be used for faster-than-light communication. These phenomena show that the universe is non-local at the quantum level, while still obeying relativity's causality. This balance is something physicists are still striving to fully understand. The precision of modern experiments has reached a level where extremely subtle effects must be considered. Gravitational redshift due to Earth's gravity causes light's frequency to change with altitude. Atomic clocks on mountaintops run faster than those at sea level. GPS satellites must correct for both special relativistic effects due to orbital speed and general relativistic effects due to the weaker gravitational field at high altitude. Without these corrections based on the speed of light, GPS would fail within minutes. Optical atomic clocks have achieved astonishing precision. These clocks use vibrations of strontium or ytterbium atoms to keep time with accuracy such that they would not gain or lose a second in billions of years, longer than the age of the universe. Raising such a clock by just 1 centimeter can detect gravitational time dilation, measuring how the relationship between light and time varies minutely in different gravitational fields. Space missions offer unique opportunities to test light's behavior. Radio signals from the Cassini spacecraft passing near the Sun allowed scientists to measure how gravity affects light's path, with results matching Einstein's predictions closely. The Gravity Probe B mission measured how Earth's rotation dragged space-time, affecting light's propagation. These experiments show that even when space-time is warped, the speed of light remains constant. The story of measuring the speed of light is also intertwined with the search for extraterrestrial intelligence. Radio signals from potential alien civilizations would travel at light speed, meaning a signal from the nearest star system would take over for years to reach Earth. The Breakthrough Listen project analyzes signals from millions of stars, with researchers aware that any detected signal is a glimpse into the past. Sent years or even centuries ago, advances in quantum computing also depend heavily on our understanding of light. Photonic quantum computers use individual photons as qubits, manipulating them with beam splitters and phase shifters. Computational speed depends on how quickly photons travel through optical circuits, ultimately limited by the speed of light. As we move toward practical quantum computers, the speed of light is not just a fundamental constant, it is an engineering constraint. At the research frontier, scientists are exploring whether space itself has structure at extremely small scales. Some quantum gravity theories suggest that at the Planck scale, space-time may be discrete rather than continuous. This could cause high-energy photons to travel slightly slower than low-energy ones. Scientists test this idea by observing gamma-ray bursts from billions of light-years away, but so far, no evidence of such quantum foam has been found. The cultural impact of understanding the speed of light extends beyond science into philosophy and human consciousness. Before knowing light has a finite speed, humans lived in a universe of instantaneous connection. Stars in the night sky were immediately present. Now we know we are seeing ancient cosmic history. Some stars visible tonight may have died long ago. Their final light is still traveling toward Earth. This awareness fundamentally changes how we understand our place in space and time. Artists and writers have long explored the implications of these insights. The rise of science fiction was partly inspired by the understanding of light's finite speed, imagining faster-than-light travel to overcome cosmic isolation. The concept of the light year entered everyday language, giving us a new way to grasp the vast distances of the universe. When Carl Sagan spoke of billions and billions of stars, he was describing light's journey across unimaginable spans of space and time. The precision required to measure the speed of light is demonstrated by another extraordinary experiment. Scientists used a tower only 20 meters high to measure the gravitational redshift of light traveling in Earth's gravitational field. As light climbs against gravity, it loses energy, shifting its frequency toward the red. This effect, predicted by Einstein, is extremely tiny. Detecting it over such a small height difference required frequency measurement precision to 18 decimal places, a level we can now routinely achieve. The finite speed of light also shapes the large-scale structure of the universe. During the inflationary epoch, the universe expanded faster than light. Space itself stretched, carrying matter apart. This did not violate relativity because no information traveled faster than light through space. This rapid expansion meant some regions of the universe never had causal contact, explaining why. The physical properties of distant regions can differ. Recent discoveries show that light's interaction with matter is more complex than early scientists imagined. Metamaterials can have negative refractive indices, making light appear to travel backward. Scientists have also created acoustic black holes, devices that trap sound, much as gravitational black holes trap light, helping us understand the origin of the cosmic speed limit. In wave physics, the quest to measure the speed of light also connects to one of humanity's oldest questions. Ancient astronomers wondered whether the universe is infinite. Today we know there is an observable universe defined by how far light has traveled since the Big Bang. Beyond this cosmic horizon, there may be infinite space, but since its light cannot reach us, we can never observe it. The finite speed of light draws a boundary between the noble and the unknowable. Life as we know it exists in a Goldilocks zone, determined by the speed of light. The search for physics beyond Einstein's theories continues, often focusing on light's behavior under extreme conditions. Near black holes, light follows paths that would be impossible in flat space. In the ergosphere of a rotating black hole, space itself rotates faster than light relative to a distant observer. Yet locally, the speed of light remains constant. These extreme environments test our deepest understanding of light speed as the universe's ultimate speed limit. Quantum field theory reveals that the speed of light arises from deeper physical principles, virtual photons mediating the electromagnetic force can temporarily exceed light speed due to quantum uncertainty, but such excursions are limited by the uncertainty principle. The faster a photon travels beyond c, the shorter its existence. Real photons carrying information always obey the light speed limit. This shows how quantum mechanics and relativity work together. To maintain cosmic consistency, the development of attosecond science has opened new frontiers. Scientists can now watch electrons moving inside atoms, chemical bonds forming, and the first steps of photosynthesis. These ultra-fast measurements rely on precise knowledge of light's oscillation frequency, turning light's wave nature into an exquisitely precise clock. The speed of light determines scales from atoms to galaxies. The characteristic size of a hydrogen atom is related to the speed of light via the fine structure constant. The scale of the observable universe is essentially the product of the speed of light and the age of the universe. One constant defines the dimensions of reality across all scales. The interaction of light, speed, and gravity produces some of the most exotic phenomena in the universe. Gravitational lensing has become a key tool for mapping dark matter and studying distant galaxies. The first exoplanet discovered via microlensing relied on precise calculations of how light bends around stars. All these observations are based on understanding how light behaves in curved space-time. The quest to understand the speed of light also reveals profound truths about information itself. Information theory, developed by Claude Shannon in the 1940s, shows that the limits of information transmission are set by channel capacity and noise. The speed of light sets the ultimate limit for information transmission in the universe. No matter how information is encoded, it cannot travel faster than light. This cosmic speed limit constrains not only physics, but also defines what knowledge and communication mean in our universe. Measuring the speed of light has also led to seemingly magical technologies. LiDAR systems fire laser pulses at objects and receive reflected signals to create high-precision 3D maps. They help self-driving cars navigate and to enable archaeologists to discover ancient cities hidden under jungle canopies. Every calculation in these technologies depends on the fact that light travels at exactly 299,790 to 0.458 kilometers per second. Even a tiny error in this value would make these technologies impossible. Recent experiments with twisted light have opened new frontiers. Scientists can create light beams carrying orbital angular momentum, beams that rotate like propellers as they travel through space. Such beams can carry more information than conventional light, potentially revolutionizing communications. Yet even these exotic forms of light obey the cosmic speed limit. No matter how we shape, twist, or encode light, information cannot travel faster than c. The connection between light speed and causality is deeper than most realize. In particle physics, virtual particles may appear to break the light speed limit, but only within the framework of quantum uncertainty. The more a virtual particle exceeds light speed, the shorter its existence. This creates a fuzzy boundary where quantum mechanics and relativity meet, hinting that at very small scales, the light speed limit may be statistical rather than absolute. Let's also consider how different environments affect light propagation. Light travels about 75% of its vacuum speed in water, and only 41% in diamond. But interestingly, light does not truly slow down upon entering these media. Photons are constantly absorbed and re-emitted by atoms, creating the appearance of slower speed. Between interactions, photons always travel at c. This shows that the speed of light as a cosmic limit is more fundamental than any material property. The discovery of Cherenkov radiation provided visual evidence for relativity. When charged particles travel through a medium faster than light does in that medium, they produce a blue shock wave, the optical equivalent of a sonic boom. Nuclear reactors glow blue because of this effect. This seems to violate Einstein's speed limit, but it does not. Nothing travels faster than light in vacuum. This phenomenon helps scientists detect neutrinos, earning the 1958 Nobel Prize in Physics. Historical errors in measuring the speed of light have also provided valuable lessons about the scientific method. In 1897, Edward Bennett Rosa used a rotating mirror method and obtained a value significantly different from the accepted one. Instead of ignoring the discrepancy, he carefully rechecked his procedure and found a calculation error. His willingness to admit mistakes and document his process in detail helped later scientists avoid similar pitfalls. Science advances not only through successes, but also through careful analysis of failures. The speed of light also influences the search for dark matter. Space telescopes have revolutionized our ability to study light across the full electromagnetic spectrum. The Hubble Space Telescope observes ultraviolet, visible, and near-infrared light. The Spitze Space Telescope studies infrared radiation. The Chandra X-ray Observatory detects X-rays. Light of different wavelengths travels at the same speed, but carries different cosmic information. By combining observations across the spectrum, we build complete pictures of celestial objects, all based on the constancy of the speed of light. The birth of special relativity came from taking seriously the idea that the speed of light is a universal constant. Einstein realized that if all observers measure the same speed for light, then space and time themselves must be flexible. This was not a mathematical trick. It was a deep insight into the nature of reality. Time dilation length contraction, and mass energy equivalence all follow logically from the constancy of the speed of light. These experiments do not violate the light speed limit, but reveal the rich, complex behavior of light within that limit. In 2015, LIGO's first detection of gravitational waves showed that space-time ripples travel at sea exactly as Einstein predicted. In 2017, scientists simultaneously observed gravitational waves and light from a neutron star merger. Both arrived at Earth after traveling 130 million light-years. Almost simultaneously, this consistency between independent measurements strengthens our confidence in the speed of light as a fundamental physical constant. The story of measuring the speed of light also reveals something profound about human nature. We are pattern-seeking creatures who refuse to accept that's just how it is as an answer. When Galileo failed to measure light speed with lanterns, he did not conclude it was impossible. He realized better methods were needed. This relentless curiosity, this refusal to accept limits, is the driving force behind all scientific progress. Each generation builds on the failures of the previous one, turning yesterday's impossibilities into today's routine. Modern quantum cryptography relies entirely on the properties of light. Quantum key distribution uses individual photons to transmit encryption keys, theoretically making them unbreakable. Any attempt to intercept a photon instantly changes its quantum state, revealing the eavesdropper. This security is based not on computational complexity, but on fundamental physical laws. Today, banks, governments, and research institutions are beginning to use quantum networks, turning light speed and quantum mechanics into unbreakable codes. The development of the optical frequency comb has revolutionized precision measurement. This laser source emits thousands of spectral lines with precise, evenly spaced frequencies, like a ruler made of light. Scientists use it to measure atomic energy level transitions with 15 decimal place accuracy, detect exoplanets by the tiny wobbles of stars, and calibrate instruments across the electromagnetic spectrum. The frequency comb turns light itself into the most precise measuring tool in the universe. Its inventors received the 2005 Nobel Prize in Physics. The constancy of the speed of light turns timing differences into distance measurements, making the invisible past visible. Perhaps the strangest consequence of light's finite speed is the relativity of simultaneity. Events that are simultaneous for one observer may occur at different times for another in motion. This is not a theoretical abstraction. GPS satellites must account for this. Without corrections for special and general relativity, GPS would accumulate errors of 10 kilometers per day. Every time your phone determines its location, it performs relativistic calculations, a practical demonstration of how light's finite speed warps space-time. Recent experiments with quantum dots have achieved extremely precise control over light emission. Scientists can trigger the emission of single photons on demand, control their color precisely, and even create entangled photon pairs. These quantum light sources are the building blocks of quantum computers and quantum networks. The speed of light becomes the metronome for the propagation of quantum information. By measuring how light travels through cosmic voids, scientists have gained clues about dark energy. Light passing through these voids experiences weaker gravitational lensing, but stronger cosmic expansion. Biological systems have evolved ingenious ways to exploit light's properties. Mantis shrimp have the most complex visual system known, capable of seeing 12 primary colors and detecting both linear and circular polarized light. They process visual information faster than any human-made system, essentially performing Fourier transforms in their eyes. At the speed of light, evolution has created organic optical computers operating at the physical limit of information processing. The development of photonic quantum computers promises to revolutionize computing. Unlike electronic computers limited by electron drift speed, photonic quantum computers operate at the speed of light, offering exponential speedups for certain problems, such as simulating molecules to design drugs, optimizing complex systems, and breaking current encryption. These machines turn the light speed limit into a core advantage. Looking ahead, proposals for interstellar communication networks rely entirely on the speed of light. The Breakthrough Starshot initiative aims to use powerful lasers to propel tiny spacecraft to Proxima Centauri. Even at 20% of light speed, the journey would take 20 years, and signals would take over for years to return. From propulsion to computation to communication design, every step is built on our precise knowledge of C. Beyond the cosmic horizon, there may be infinite space, but we can never observe it. Some cosmologists argue this makes the question of the universe's total size meaningless. We can only know the observable part. The speed of light limits not only how fast we can travel, but also the range of meaningful questions we can ask about reality. As we reach the end of humanity's journey to measure the speed of light, let us pause and reflect. What began with philosophers wondering if light travels instantaneously ended with defining fundamental units based on the speed of light. For most of human history, we believed we were at the center of the universe, with everything revolving around us. The process of measuring the speed of light has been one of gradually realizing we are not the center, but participants. We are made of stardust, observing starlight using tools forged from stellar remnants. To measure the cosmic speed limit that governs everything, we are the universe exploring itself. Today's measurement precision has reached almost absurd levels. We can measure frequencies to 18 decimal places, detect distance changes smaller than an atomic nucleus, and track time with precision exceeding the oscillation period of visible light. Yet each improvement in precision brings new mysteries. When measurements were precise enough to detect energy quantization, quantum mechanics was born. When we realized the constancy of the speed of light, relativity emerged. As we push precision to new limits, new physics awaits discovery. Consider the cosmic universality of the speed of light. Whether it's the light from a candle on Earth, gamma rays from a distant quasar, or radio waves from a pulsar, all travel at exactly the same speed in vacuum. This universality hints at a deep symmetry in the laws of nature. Every photon in the universe, regardless of its energy, origin or destination obeys the same speed limit, as if the universe has an unbreakable rule that all electromagnetic radiation must follow. Measuring the speed of light also reveals that we live in an inherently relativistic universe. Time is not absolute. Its flow changes with motion and gravity. Space is not fixed. It can stretch, compress, and bend. Mass and energy are interchangeable. These are not abstract ideas. They are practical realities we must account for. And GPS satellites, particle accelerators, and astronomical observations. The finite speed of light does not limit us. It shows us that reality is far more flexible than we ever imagined. Modern experiments continue to push boundaries. Scientists have created time crystals, challenging our understanding of thermodynamics. They have achieved quantum supremacy with photonic processors, solving problems classical computers cannot handle efficiently. They have even achieved quantum teleportation between distant locations. Each achievement is built on our understanding of light, using its quantum properties to achieve effects that seem like magic, yet are manifestations of deeper physical laws. The search for variations in the speed of light over cosmic time has become an important research direction. If fundamental constants change as the universe evolves, it would revolutionize cosmology. But so far, observations of light from ancient quasars indicate that physics billions of years ago was identical to today's. Light from the early universe travels at exactly the same speed as the light from your lamp as you read. This consistency across space and time suggests that physical laws are truly universal, not local accidents. Finally, consider this profound realization. Every atom in your body has interacted countless times with photons traveling at light speed. The carbon in your DNA was forged in stellar cores, where photons carried energy outward. The calcium in your bones came from supernova explosions, whose light still travels through the cosmos. The iron in your blood has absorbed and emitted photons. In every chemical reaction, you are not just an observer of light. You are a collection of atoms that have danced with light since the beginning. Quantum networks may enable unhackable global communication. Optical tweezers can assemble materials with atomic precision. Metamaterial cloaks could make true invisibility possible. Each application is built on centuries of effort to understand the nature of light. The philosophical questions raised by light's finite speed remain deep and unresolved. If information cannot travel faster than light, what does that mean for free will in a relativistic universe? Why does quantum entanglement allow instantaneous correlation without violating relativity? Why is there a speed limit at all? These questions blur the line between physics and philosophy, suggesting that understanding the nature of light speed is essentially understanding the nature of existence. As telescopes and detectors continue to improve, we have learned that 95% of the universe is composed of dark matter and dark energy, undetectable by light. This humbling realization shows that even our most basic measuring tools reveal only a tiny fraction of reality. Yet it is through precise measurements of light from distant stars that we discovered these dark components. Light remains our primary window into the cosmos. even as it shows us the vastness of the unknown. The legacy of measuring the speed of light has taught us about human ambition and ingenuity. From Galileo's lanterns to modern frequency combs, each generation built on the work of the previous one, turning yesterday's impossibilities into today's routines. This gradual progress, where failures are as important as successes, is the essence of the scientific method. We stand on the shoulders of giants who refused to accept the unmeasurable or the unknowable, constantly expanding the boundaries of human knowledge. Looking back on the long journey, from ancient philosophers to quantum physicists, we see that measuring the speed of light was never just about curiosity. It was about understanding our place in the universe, pushing the limits of human capability, and revealing the deep structure of reality. Every student learning about C, every engineer designing fiber optic systems, every astronomer measuring cosmic distances, all are part of this ongoing quest. All right, my friend, let's conclude our conversation here for tonight. Now, allow me to press pause for you, set aside all thoughts and inquiries, and simply be present in this moment. From here, my words will fade away, leaving only the silent tapestry of the cosmos and a carefully curated piece of pure music tuned to 430 Hz. Science suggests this frequency resonates deeply with the natural vibrations of the universe and the rhythm of life itself, soothing your nervous system and guiding you into a state of deep relaxation. Now, find your most comfortable position. Gently close your eyes, or let your gaze rest softly upon the stars. May you release all weariness from the world, letting your consciousness drift on the waves of music, floating into boundless tranquility. Good night and sweet dreams until we meet again among the stars.